Hello everyone. Today I'm going to tell you about one of the not so easy pieces of mathematics, that is complex numbers. Well, I'll be discussing the fundamentals of complex numbers. First thing to think about is what forces us to think of something like complex numbers. All have studied the quadratic formula, which states that for any general quadratic polynomial, ax squared plus bx plus c, the solution exists if and only if b square is greater than 4ac. Well, what if b square is smaller than 4ac? Does this mean that the equation does not possess any solution? No, that's definitely not the case because maths leaves no stone unturned. The equation in this case will not have any real solution. Instead, it will have an imaginary solution. And this brings us to the concept of complex numbers. Complex numbers have enriched many branches of mathematics like trigonometry, calculus, and linear algebra. The concept of complex numbers was introduced by Cardano, which was further enhanced by Bombelli, Girard, Descartes, Bernoulli, De Moivre, Euler, Gauss, and Argand. Some of the greatest mathematicians quoted that the concept of complex numbers is by far the greatest discovery in mathematics. Number is generally denoted by z. Z is equal to a plus ib, or z is equal to a plus iota b, where a and b are real numbers, and I stands for iota, which means the square root of -1. The symbol iota or I was introduced by Bombelli and plays a significant role in complex numbers. Just how a pure real number can be expressed as a multiple of 1 and the number itself, the same way a pure complex number can be expressed as the multiple of iota and a real number. Argand diagram is a special system of coordinate axes which was proposed by John Robert Argand for the representation of complex numbers. Purely real numbers lie along the x-axis and purely imaginary numbers lie along the y-axis. R is the modulus of complex number, that is, its distance from the origin, and theta is the principal argument. Practically, a real number can be thought of as a complex number, whose imaginary part is 0. The basic algebraic functions are also applicable to the complex numbers as shown. There are different forms of representation of a complex numbers. First, the Cartesian form. Second, the polar or trigonometric form. Or third, the exponential form. The notable fact here is that a relationship can be established between the exponential and the trigonometric form. This can be proved using Taylor series. Now, you must be thinking about the use of complex numbers. Well, this concept has found its use in applied sciences. It is used to study the electrical circuits, motion of electromagnetic waves, fluid dynamics, and quantum physics. In studying the alternating current circuits, the maths used by a capacitor or an inductor to change the phase difference comprise of complex numbers. Fourier transformation, which states that any function can be written in the form of sine and cosine functions added up. It is also used in Mandelbrot set. Mandelbrot is an image representing the behavior of the series Zn plus 1 is equal to Zn square plus Z naught or Z0, where Z is a complex number. A simple conclusion that can be drawn is the fact that we are pretty much surrounded by this math. The electronic devices we use are based on this mathematics. The electricity is based on this concept. The core sciences devise new concepts using this mathematics only. So we conclude that the potential of complex numbers is infinite, even though they don't exist, yet they form an integral part of the world. Thank you.